Hello, Eli. We are in section 5.7. The homework for this section is this stuff. I think I gave this to you on Thursday. The key word for this video is popcorn. So we'll ask you, if you get it, you get a high five. Sure. A prize.
We do need to have a prize. Do we actually have a prize?
Maybe I'll bring you popcorn sometime. Yeah. Okay. All right, I've decided we're going to do example 3 and example 4 and call it quits because I don't want to do any more in this section. This is taking up way too much of my time and I don't like it anyway. So example 3 we've already done. You guys might have writing on this. So if you have this written down already, great. Let's just go through.
We didn't finish the video.
Okay, then let's just go through example 3 and we'll just talk about what some of this stuff means. Okay, so we are graphing velocity versus time. Now, velocity is second derivative, so keep that in mind. Okay? Or not second derivative. Velocity is the first derivative. It is velocity is the derivative of the position. So, deriv of the position function, which they call it s for some reason. S of t, okay? So we've got our position function t, or s of t. We take the derivative of it, we get the velocity, okay? So now we have velocity, and they're graphing velocity versus time, okay? So as time is going to the right, as we are moving along to the right for like 4 seconds, I don't know if this is in seconds, but as we go 4 seconds along, the velocity is going up, and then it's going back down, right? Which means we are increasing velocity. Like this point down here, I think I used like 0.2 or something, right? Like I have a 0.2 velocity and then I get all the way up at 2 seconds and I am at max velocity, which is 1. I don't know if that's 1 mile per hour. I don't know if that's 1 meter per second, whatever it is, but that's my velocity. It caps out at 2 seconds. And then now I'm decreasing, okay? Because this whole thing is above the x-axis, that is representing me moving in the positive direction. So a lot of people think velocity being positive is going up, like launching something out of a gun, right? Which it could be, right? It could be launching something out of a gun, or we could think of it as moving to the right, okay? And this whole time, even though I'm going uphill and then I'm going downhill, I am still moving to the right the whole way. It's just at this halfway point, like I'm speeding up and then I'm slowing down, right? Until I get to that 2 second mark, I'm speeding up and then I'm slowing down. As you usually do, if you're going down the block or whatever and you have a stop sign and a stop sign, you're going to speed up and then halfway, like through the block, I'm going to slow down to get to the next stop sign, right? So that's how that's going to work. But this is how this works. Now, I have to figure out, if I'm looking at like distance-wise, how far have I gone? I know I've gone for 4 seconds, but how far have I gone?
2. 4.
How do you figure that out?
1/2 base of type.
Yeah, I'm looking at area. Like when we've done integrals and we've tried to find the area underneath of the curve, that's another way of representing distance, right? Area under of curve is distance. And so the base of this triangle is 4, the height is 1, so 1/2 base is 4, height is 1. I know that I'm going a distance of 2, whatever units we're in, 2 feet, 2 meters, 2 miles, whatever, right? That's how far I've gone, okay?
Hold on.
That's the same
Okay.
for both.
Base times height. Base is 4.
Will be negative.
And that's the what? The distance?
That's the distance, yes. Distance is like the integral,
Area.
right? Okay, is the area, okay? Now, what's the difference here? This is also going to have a distance of 2. So I've gone 2 for a distance. I'm moving to the left. I'm still increasing in velocity because here is negative 0.2 is slower than right here. Here I'm going fast, right? And so I'm speeding up technically. So this going downhill is still me speeding up. That's hard to think about, right? But as that goes down, I'm still speeding up because a -1 speed is going to be a faster speed than a 0.2 speed or whatever, right? So I'm still speeding up and then I'm slowing back down again. But the difference is, since he's below the x-axis, that is me walking this direction. I'm walking to the left,
Got it.
okay? Or something is falling toward the earth. Right? That's why we represent negative velocity. Okay? So again, we're going for 4 seconds, but we're going a distance of 2, whatever it is. 2 feet, 2 meters, 2 miles, whatever. Right? Okay? Now this one,
So we're just zigzagging.
We're-
right then left.
kind of, yeah. So here, since he's up above, he is going to the right first. We're going to the right for 2 seconds.
Oh wait, his distance is 4. His position is 0, right?
Okay? Let's talk about just this little hump right here. How far have we gone to the right?
1, 2.
2.
2 seconds. 2 seconds, but what's the area under here?
1.
1. That's going to have an area of 1. So I have gone 1, let's call it feet. I've gone 1 foot to the left, right? Okay? And again, I'm speeding up and then I'm slowing down, right? Speeding up, slowing down. Speeding up, slowing down, speeding up, slowing down. That's why we have going up and then down. Then this bottom half right here has an area also of 1, right? But I stopped here. Now look at what's my velocity going to be when I stop?
0.
0. Does my velocity 0 when I stop?
Yeah.
Y'all, right there, okay? And now I have turned around and now I'm walking back this direction, 1 foot,
We're right where we started.
which means we're right where we started.
So
And that
distance
makes
0.
sense because if we would do this as an integral, wouldn't those areas cancel each other out? Yeah, a -1 area and a +1 area would cancel each other out. That's just talking about,
Our position is 0, but our distance is 2.
okay? Now, here, our distance, maybe let's talk about this. Our distance is 2 still. But let's talk displacement.
Displacement is 0.
But displacement is 0. I have gone, displacement is just where you ended versus where you started.
Right.
I am right on top of where I started. Distance, though, I have done some work in between. If you just give me displacement, it looks like I've just been sitting there and doing nothing, right? But I actually did some work. I actually still went 2 units. What's the displacement here?
4.
It's like walking.
No, what's the displacement in the middle one? Still 2.
Oh.
Still 2. The displacement is still 2. They might say -2 because it's 2 units to the left because I'm two left of where I was to begin with. Okay, but it's still gone 2. Here, my displacement is 2 to the right or
have to
just
specify
+2.
direction.
I don't know that they necessarily care. You might do +2 and -2. It doesn't matter. But okay, understand the difference between displacement and distance and how the graph works and stuff. Okay, yeah, not too bad. Yep, sure. Okay, so that is going to be similar to like number 1, I think, on the homework.
Getting so much better.
Possibly. Possibly. Are you writing with your right?
Yeah, the first
No?
two,
Right with your
I
left?
like made an equation and that was kind of stupid. And I actually did like the antiderivative thing, like
Yeah.
the integral.
Nice.
And then after that, I was like, no.
Five
And
and
then
six.
I just did the triangle thing.
Nice. Nice.
He's a
I don't know
hardcore
why.
judge today.
Okay.
Okay, let's see, for example 4 if we can get through this. I don't know. There's a lot of words going on here. Let's see what we've got. Okay. All right. Suppose that an intergalactic spacecraft uses a sail and the solar wind to produce a constant acceleration. Okay, so I'm going to say A of t is equal to 0. Whoa. A of t, acceleration, is equal to 0.032 meters per second. We'll just leave the label off for now, okay? Now, they're going to ask me some velocity questions, and they're going to ask me some position function questions, okay? So, we know that to go from position to velocity, I take the derivative, right? Okay? And and to go from velocity to acceleration, I also take the derivative, yeah?
Isn't that the second derivative?
That's the second, that would be like the second derivative of the position.
Position.
Yep, so it's the derivative of velocity or second derivative of position. Now if I'm going, so now I'm starting with this guy and I'm working back this direction, right? So now I want to do the antideriv. And I want to do the antideriv again to get back to the original. And so this will tell me.
3, 2.
Is there such thing as a second
X, T.
antiderivative?
T
Yeah,
plus
that's
C.
kind of like what we would be
Is
doing.
that what we're doing?
What? T plus what? Yeah, you're right. Okay, so let's talk about this. If I'm trying to do this as an antiderivative, if we want to like set it up officially, it would be 0.032 d what? dt, because they want it in terms of time. Okay, so not a definite integral. This is an indefinite integral. What does that mean?
I don't remember.
We don't have little number thingy things to plug in, okay? All right, so when we take the antiderivative, this is going to be 0.032t plus c. Now, the problem with doing the antiderivative again is I don't know what that c number is. So let's see if we can figure out some stuff that will help me figure out what that c is, okay? So I have v of t is equal to this junk plus c, okay? Assuming that the spacecraft has a velocity of this much when the sail is first raised. Okay?
10,000 is
Or
Now, this is saying the velocity equals 10,000, okay? When the sail is first raised. But what does sail first raised mean? That means time is 0. So velocity, I can plug 10,000 in here, and I can plug 0 in for t, and then that means c is going to be 10,000, right? If I plug 10,000 in for V, time is 0, that means my C is going to be 10,000.
Wow,
Okay.
That makes so much sense.
Yeah. So they have to give you that stuff. Now we're gonna do some more. So my official equation for V of t is going to be 0.032 t plus 10,000. Okay? And then I'm going to take the antiderivative of that to find the position function. So I'm gonna do the integral dt again, that stuff, and then let's do this stuff. Okay. So what's the antiderivative of 0.003 or 0.032 t?
Wait.
Just do 0.032 on top.
0.032 over
2.
2, right?
T
T
squared.
squared.
So that's
Right?
10,000 T.
Plus 10,000 T plus C. Don't forget plus C. Okay, so that's what he will look like. Now, we can reduce this. This is actually going to be 0.016 T squared, right?
Yeah. What?
0.01.
Oh, how are we going to find that?
Wait, what? Repeat that?
We're gonna
What
find
is
C.
the answer?
0.016 T squared. You're just finding the antiderivative
Plus 10,000
of your last.
plus C.
Okay, now, they don't tell me what C is for this one.
Would it be
When
like
the sail is first raised, how far will this?
The position function tells how far.
In 1 hour. Can we use
1 hour
that?
is 30. I don't know. We don't T. Or we don't know.
We don't know T yet. Okay, but how do we need to figure out what goes in for C.
1 hour is
Like, we have to figure out what C is.
well, 1 hour is 3600 seconds.
Oh wait.
What?
0.
Will C be 0?
Yes.
Well, it says T is 0.
But why?
If T is 0, like if I plug 0 in for T, I have to have a number to plug in for S of T. S of T is the distance I have gone at 0 seconds. How far have I gone at 0 seconds?
0.
Nowhere.
0, so C is 0. Yeah, do you see how that works? Okay, so our official final function, maybe I should write these down. Acceleration is 0.032. We're accelerating at a constant rate. That's why there's no variable with the acceleration. But the velocity is increasing velocity at 0.032 t plus 10,000 because we initially are going 10,000 whatever meters per second. And then S of t is 0.016 t squared plus 10,000
So we just plug in that now.
t. Yep.
3,600.
And we don't have a C on the last one, okay? It says, how far will the spacecraft travel in 1 hour? Hold on. 1 hour. Do we plug 1 in or do we plug 60 in?
3,600.
What time
It's
is it?
meters per second.
Or 3,600?
3,600.
3,600, you're right.
None of the above.
Yeah, none of the above.
0, 1.
How far will the spacecraft travel? Okay, when we're asking for how far, which equation are we plugging into?
The S of T.
S of t. So we're plugging t equals 3,600 into there and
Ready.
finding S of t. Yep, I'm ready.
362.
362. 07
360.
360.
Yep.
Woo! Meters?
Yes.
That's a lot of meters.
And then
36,207,360 meters.
I need to rewrite that. That was not a number.
2 what?
That's how far I have gone
Okay,
after
now-
1 hour.
we need to do.
And then it says, and what will its velocity be at the end of this hour?
Now we need to plug it back into the other one.
So now we want velocity here. So I'm going to plug 3,600 in for velocity and get what our velocity or speed is at that point.
10,115.
What?
I don't know. Did I do that right?
Yeah.
Am I plugging into the second equation?
Yeah.
Yeah.
Okay, so 10,115.2.
10,115.2
Yes.
meters per second. That seems like really fast. But what are we talking about? A spacecraft. Yeah. I'm going to guess that that's probably booking.
Yay! That one?
That wasn't too bad.
That actually makes
yeah,
sense.
not too bad. We like those, right?
Yeah. When we asked what this has to do with
Yeah.
real life.
Yeah.
Spacecraft.
Yeah.
Spacecraft.
Spacecraft. Or anything else. I mean, like the number, I don't know, any of these other ones are like, the baseball is being thrown at blah, blah, blah.
By Nolan Ryan.
What is the velocity and acceleration of the ball? Or the ball is accelerating at this rate. What's the velocity?
Plays for the Mets, guys. Number 36.
Okay. All right. So let's skip those examples because I want to move on to the next section eventually, but not today.
Say that somewhere?
It's
So what's our plan for the rest of the week?
I don't know. Probably nothing. We're probably doing prom stuff the rest of the week.
Yay.
There is one more section that I want to do in this chapter, and it is, we're going to skip a section. We're going to skip two sections, actually.
312.
312. We're going to skip two sections. We're going to skip 5:8 and 5:10. And we're going to do 5:9, which is use substitution with definite integrals, where you're plugging numbers in. It's not bad. It's like the same as what we've been doing already.
Yeah.
But there is one little shortcut that you can do.
5, 7. Okay, and then I also need to do.
You don't have to do the plus C part.
What is it? Page
Right.
303.
You don't have to blow the plus C part.
303.
Okay, there we go. We're done with that stuff. All right.
16.
Give me just